At this point, it might be helpful to do a quick review of a lot of the equations we have regarding electric force, electrostatic potential energy, electric potential, electric field, and so on for discrete charges. So here we have two discrete charges in our first case. Let's use this as an example for calculating how would we determine what's the mutual force of attraction between the two. So force is a vector quantity, so we can draw a vector here. We can say this one is, the positive charge is Q1, the negative charge is Q2. So this is the force that charge number 2 is exerting on charge number 1. By Newton's third law, the force that charge number 1 exerts on charge number 2 is equal and pointing in the opposite direction. But what is the value of that force? The magnitude, anyway, is K Q1 Q2 over R squared. This is known as Coulomb's law, and of course this is review. If we want to write that in its full form, then we need to express it as a vector quantity. So we put the vector symbol over F, K Q1 Q2 over R squared. So to make the right side of the equation a vector, we need to multiply this times a vector with a magnitude of 1. So we make a unit vector R hat, and there we have it. So clearly we're talking about two charges that are separated by a distance that we identify as R. We could also figure out what's the stored electric potential energy. Because they are exerting a mutual force of attraction between the two, then when released from rest, that attraction is going to cause both of them to start to accelerate towards their common center. And so they're going to gain kinetic energy. Well, where does that kinetic energy come from? Energy cannot be created or destroyed, so there's a conversion of electrostatic potential energy into kinetic energy. Exactly how much electrostatic potential energy is there due to each charge being separated by a distance of r? In that case, we say U is equal to K Q1 Q2 over R. We do not put a vector symbol on that because it's not a vector, so there's no r hat on the right side of the equation. This is just a scalar equation, and there you have it. Now, if we only have a single charge, so I don't have to put a subscript 1 or a subscript 2 on this. If it's just a single charge, then we just call it Q. If we pick any point in space, maybe we want to know here, maybe we want to know here, or here. Well, pick any one of these and then say the distance to that point in question, maybe we call this point P, is a distance of R. Now we can figure out how strong is the electric field at that point, right? So if I were to put a second charge here, if this does become a Q1 and I place some Q2, what would the amount of force on Q2 be equal to? Well, the electric field would be whatever that force is divided by the charge of Q2. Or we can say it like this. We just define electric field as being force per unit charge. And so if that's true, the electric field is equal to KQ over R squared. And because force is a vector quantity, then electric field must also be a vector quantity. Likewise, we can define a quantity known as electric potential at point P. And it's equal to, by definition, not the force per unit charge, but the amount of potential energy per unit charge. So the electric potential is KQ over R. Okay, so we have 4 equations. One for force, one for potential energy, one for field, and one for electric potential. If you have several charges, then we can find the net electric field or the net electric potential by applying the principle of superposition. So the equations don't change, we just have to use this equation multiple times, or the equation for electric field multiple times, and then just add everything up. So all these electrostatics equations then are listed here again. And it might be helpful for you to copy these onto a note card. It's kind of nice to have these all in one place. But I do want to take the time to point out that you've seen equations of this form in our study of gravity in the previous semester. We saw equations that match up. For example, Coulomb's law finds the force between two charged particles. Newton's law of universal gravitation gives us the force between two massive objects. The difference here is when you have two positive charges, then the force is repulsion. But if you have, well, there's only such thing as positive mass. There's no negative mass. And so like masses attract, as seen by the negative sign in this equation, whereas like charges repel, seen by the positive sign in Coulomb's law. Okay, then electric field is defined as being force per unit charge, so I should write 3 lines in my equal sign. Electric field is equal by definition to force per unit charge, in the very same way that gravitational field is equal by definition to force per unit mass. So if that's the case, then electric field from a single charged particle can be solved for as kq over r squared, in the very same way that the gravitational field due to a single massive object is, gm over r squared. Or to be correct, the negative sign here is just a way of saying that gravitational field lines point toward massive objects, whereas electric field lines point away from positively charged objects. Electrostatic potential energy is an equation that shares the same form as gravitational potential energy. And again, we see this difference between positive and negative signs. Now here's where the comparison sort of disappears. There is no quantity that we studied when we were learning about Newton's law of universal gravitation that compares in any way to this thing known as electric potential. Because electric potential is energy per unit charge, and again this is equal to by definition, then the units for electric potential are joules per Coulomb. Well, we didn't have anything we studied in gravity that was joules per kilogram. What symbol would you use for? I don't know, we can make up some really kooky looking symbol. Okay, we say that's equal to, by definition, gravitational potential energy per unit mass. Yeah, then the units would be joules per kilogram, and I suppose this weird quantity would be solved for as negative gm over r. But we just didn't make that definition, and so we can't make that comparison. But otherwise, the rest of these equations for electrostatics can be related back to prior knowledge regarding our study of gravity. Well, these equations won't always apply. These are really only useful when we have discrete charges. 1, 2, 3, 4 individual charges that I can identify. If charges instead spread out as a distribution of charge across some shape, whether it's a sphere or a rod or you name it, then we need some other equations to solve for electric field and electric potential. Generally, let's pick a point here. Maybe we want to know at this point P what's both the electric field and the electric potential. So there are 2 ways we might find the electric field. One is a brute force method in which we just apply Coulomb's law and the superposition principle. We divide the charged rod up into a bunch of little bits. So if the charge distributed across the rod has a total charge capital Q, then we divide it up into a bunch of small parts dq, and if that dq is at a distance of r from this point in question, then there's a little bit of electric field equal to k dq over r squared. So if I want to get the total electric field, I just have to add all of these up, right? And so that's what we mean by the brute force method. The other method comes from Gauss's law. There's enough symmetry in this distribution of charge that we can make a cylindrical Gaussian surface. Gauss's law says the total electric flux through this Gaussian surface is equal to the amount of charge inside the Gaussian surface divided by the permittivity of free space. Well, there's also 2 methods that we generally would use for solving for the electric potential at this point P. And the first one is also a brute force method. We would say the overall electric potential can be found by adding up all the small contributions from each individual dq. And so it's just the integral of k dq over r. So the second method comes from the fact that change in potential energy is always equal to negative the work done by a conservative force, and electric fields exert conservative forces. Okay, and then we also know that work is equal to the integral of f dot ds. Electric potential, or at least change in electric potential, is equal to change in potential energy per unit charge. So I guess it must be equal to negative work per unit charge. So it's got to be equal to negative the integral of f over q ds, but f over q is electric field. So we have change in electric potential, which would be like a V2 minus V1 change in, is equal to negative the integral of E dot ds as we integrate along a path that takes us from point 1 to point number 2. Now this equation becomes useful if we create a frame of reference where we let the electric potential at point 1 on our path be equal to 0. Now we can get rid of this negative sign if we just switch the limits of integration, and so we get the electric potential at point 2 along our path is equal to positive the integral as we move from 2 to 1 E dot ds. That's the second method for solving for V. So if you want to write all these equations down, like I said earlier, probably not a bad idea, so that you have them all in one place as we continue to work through this unit of study.